Okay, welcome to lesson 3 as we talk about electrochemical reaction kinetics. Today's goal is for us to draw a link between an applied potential and the current that we experience. And we also want you to make you familiar with kinetic analyses that are done in electrochemistry, like the TOEFL analysis here on the right. So first, let's talk about homogeneous reaction kinetics. In the diagram, I want you to notice the two parabolas. These are energy surfaces. And if you notice, if we're moving from the energy surface on the left to the energy surface on the right, to get there, we have to reach the point where the two meet, and that's known as the transition state. Now, we can draw our movement from the equilibrium or the bottom of the parabola up to the transition state as the change in Gibbs free energy with a double dagger. If we're going to the right, then we'd say that's the forward change in Gibbs free energy. And if we're going to the left, then that would be the backwards change in Gibbs free energy. So let's say we have species A and species B. There's a reaction, and they're in equilibrium with each other. So we can write the forward rate expression as the forward rate constant multiplied by the concentration of A. And we can write the backwards rate constant as the backwards rate expression as the backwards rate constant multiplied by the concentration of B. Well, we can then write the net reaction by getting the difference between the forward rate and the backwards rate, and we can establish what the equilibrium is. So at equilibrium, the rates will be equal to this constant and the concentrations will be equal to this constant. And how we get there mathematically is we say at equilibrium, the net rate of reaction is equal to 0. You might recognize this equilibrium coefficient because it shows up in the Nernst equation. We can also write out the reaction coefficients with the Arrhenius expression, where we have a pre-exponential factor, that's that A sub k, and then we have the exponential term where we have energy of activation, the universal gas constant, and temperature. And I'll dive into the math a little bit closer, but I'll just say here that the energy of activation we can approximate as the change in Gibbs free energy to the transition state, though you'll notice that the pre-exponential factor changes when we make this assumption. So when we move to heterogeneous electrochemical kinetics, we get a little bit more complicated. We're going to start with fewer assumptions in this case. So let's say we have an oxidative species that's being reduced. And so in this case, in the net rate expression, we're going to include the activity of the oxidized species and the activity of the electron and the reduced species. Now you'll notice that this is for a single electron transfer. And we're going to make a few other assumptions. So we're going to say that the activity of the electrons is equal to 1. And we're going to say that the activity coefficients of all species is equal to 1 as well. So that way we can write concentrations instead of activities. So we have our new rate expression and the Arrhenius equation, and let's see how we get from an energy of activation to the change in Gibbs free energy to transition. So the energy of activation is equal to the change in internal energy to the transition state. And through thermodynamic definitions, we know that the change in internal energy is equal to the change in enthalpy minus the PV work. But we're going to assume that the PV work is equal to 0, or there's no change in pressure, no change in volume. And that allows us to say that the energy of activation is approximately equal to the change in enthalpy to the transition state, which is then equal to the change in Gibbs free energy plus temperature times the change in entropy. Now what we're going to do is we write out the Arrhenius equation again. We group the pre-exponential factor and the term with entropy inside of it. So then now we have a new pre-exponential factor, and then we have an exponent with the change in Gibbs free energy to the transition state. So here's our new Arrhenius equation. Now we're going to take this new Arrhenius equation and we're going to write out what the Gibbs free energy of transition is a little bit more closely. So for an anodic species, we're going to say, there's some reference state. There's this term with the transfer coefficient. We're going to multiply that by Faraday's constant, and then multiply that by the difference between the potential and the formal potential. Now you'll notice that this is for one electrode reactions, and that there's a slight difference between the anodic term and the cathodic term. So we take these, we write out our Arrhenius equations, which is how we calculate our rate constants. And now let's make a few more little changes. So we're going to find little f, as Faraday's constant divided by the universal gas constant and temperature. And then we're going to define this little equilibrium rate constant as the rate constant that is experienced when there's no overpotential. And so here are the mathematical definitions of it. Making those two changes, that allows us to write out much simplified terms for the rate constants, both the forward and the backward rate constants. And you'll notice both of them have the equilibrium rate constant inside of them, and both of them have this alpha, or the transfer coefficient, inside of them. So let's talk about the transfer coefficient for a little bit, because we haven't yet. Well, what we're going to do is we're going to draw out our two potential surfaces here in the top left. Two energy surfaces. And we're going to say we move from the red state to the blue state. And how we move this is we change the potential of our electrode. And so we move from the formal potential to something that isn't the formal potential anymore. And then we zoom in on where all of our curves intersect. And here's the diagram where we're all zoomed in, so everything's linear at this point. And we do a little bit of basic geometry, and that lets us define what alpha is. And so if we look over here on the right, we can see that what alpha is talking about really is the relative shape of the energy surfaces for the product and for the reactant in our reaction. And if those energy surfaces have the same slope when we zoom in on them, then our alphas would be equal to 1/2. But if they're unequal in some way, then our alphas begin to change away from that 1/2. So let's put it all together into this nifty expression here. And how we're going to do that is we need to correlate between the rate of reaction and current. So we define the relationship here on the top line. And then remember, we're assuming that there's only one electron being exchanged. So in that case, n is equal to 1. We write out our rate expression here, set it equal to the current divided by Faraday's constant and the area of our electrode. We rearrange so we have the current on one side, and then we expand out our rate coefficients, or our rate constants, into the following terms. So we have the current is equal to Faraday's constant times the area of our electrode multiplied by the equilibrium rate constant. And then we have that multiplied by the concentration of our reduced species at the electrode. That's what that x equals 0 means. And that's raised to an exponent term, and that exponent term includes the transfer coefficient, includes Faraday's constant, temperature, and also the change between the difference of potentials. Okay, great. So we have this expression, and what I want you to do now is go ahead and pause the video and answer these two questions. And in a few seconds, I will give you my answers for them. Okay. What assumptions are made in the derivation of our expression that's relating the current, the equilibrium rate constant, and potentials? So we said that n is equal to 1, or in other words, the stoichiometric coefficient for electrons is equal to 1. We said that the activity of electrons is equal to 1. We said that the activity coefficients for the oxidized and reduced species are equal to 1. And we assumed that the activation energy is approximately equal to the change in enthalpy to the transition state, or in other words, there's no PV work. Next, what's the meaning of the transfer coefficient? Well, it's a measure of how the activation energy for the forward and the reverse reactions or backwards reactions change as we change the potential of our electron. Great, so we hope you'll join us for our next little video on a few useful kinetic relations.